Yeah, welcome back to the second lecture for today. Today we want to actually calculate numerically, not numerically, analytically, the positions of the ATI peaks. And the reason we want to do this is not because we want to find out, we actually know this already, but this really is one of the few examples that can be done without a computer here. And it helps seeing that we really understand what's happening, yeah, that our model makes sense. And the insight that we get at the end is actually quite instructive. And the same method also applies to recollision electrons, and in particular high harmonic generation, where this whole phase business is even more important. And staying with a above threshold ionization, this is actually really interesting for few cycle pulses, as we will see at the end. Okay, now let's get down to business. Can you show the iPad? Yes. Okay, so we have here 7.2 ATI peaks. Okay, well, points 1 and 2 is what I just said orally, and what we're doing now is we examine 2 times that are close together in adjacent cycles. 2 times T and T naught, T naught and T naught plus T. Well, let me sketch this. So this here is our electric field. I'm not happy with it. I'll draw it again. Yeah, this is better. Okay, so we examine 2 times here. Yeah, this one and that one. So one we call T01 and T02, and they're spaced by exactly the optical period T. And at each of these times, we launch a trajectory. Yeah, so this one here, this would look something like this perhaps, and then this one here, this would look something like this. And we know from construction that at the end of the laser field they will have the same final momentum. Okay, so we examine these 2 times, and we choose T naught such that that we have an ATI peak. Yeah, so ATI peaks, this means we have an interference maximum. And that means that the relative phase, or the phase difference of the 2, must be a multiple of 2 pi. Yeah, and of course we have that the drift energy is 2 UP times sine square omega 2 naught. And now we said that this should be an ATI peak, so we can write it as n times, we can write its energy position at n times h bar omega, and I just write here plus delta E. And we actually know that delta E would be minus EIP minus UP. But here I just write delta E, and we'll see what comes out of this calculation. Okay, so the next step is to calculate the phase for these two trajectories. So calculate phi 1. Yeah, so this would be S1 over h bar. So the action of the first trajectory, 1 over h bar. And then we need to integrate over the Lagrange function of this first trajectory. So here this would, we call this x1 of t dt. So this would be this one here. And we have this one here as well. And we calculate the same for the second trajectory. Okay, so how far, actually in what limits do we need to calculate this? Yeah, so until t naught, yeah, until this time, both electron, so in both cases the electron is bound in the ground state, so they experience the same action. And then after the end of the pulse, there's no more field, so there's also no more. Yeah, so the only interesting times are between the emission of the first electron. Yeah, then we have this time here in which the first electron actually propagates in the continuum, and the second one is still bound. And after that, they both propagate in the continuum, but this one has already traveled a certain distance. Yeah, so therefore, we need to see if that makes a difference or not. And it also has some, it already has some velocity, whereas this one does not. So there we need to be careful. Yeah, but after the pulse is over, they're no longer accelerated, and by construction we know they have the same final state, so they just drift away with the same velocity. And therefore we need to integrate between t naught and the end of the pulse. T naught, Te, where Te is the end of the pulse. And by the way, if you think of the simulations that we did, there we often used a sine square envelope for the pulse, and this is one of the reasons why. Because then with the sine square envelope, you actually have a defined time at which the pulse is over. If, however, you have a Gaussian pulse, then you need to decide where the pulse is over, because it never is. Okay. Okay, so we discussed the limits, yeah. So I just write before T naught and after Te. There is no difference in the trajectories. So we don't need to calculate these. Calculate outside T naught, T end. Okay, so let's write down the Lagrange function. Yeah, so the Lagrange function is the kinetic energy. Maybe I used T before, but maybe this is not very useful because we already have T for the tunneling rate and the optical period. So let's not use it for the kinetic energy, but simply write energy kinetic minus V for potential energy. Okay, so before tunneling, the electron is bound in the ground state, and in the, well, so we use the strong field approximation. Yeah, so before tunneling, the electron is bound and doesn't propagate, so the kinetic energy is 0, but the potential energy is given by the ionization potential. Yeah, so that's minus EIP. And so since there's a minus here, the Lagrange function before tunneling is simply EIP before tunneling. And then we assume tunneling to be instantaneous. And after tunneling, yes, kinetic energy is, of course, a half m times v squared. And then we need the potential energy. The potential energy is E times x. So it's the but we need, do we need a minus? I have here a plus, but I'm not sure that if the plus or the minus is correct. But we get the correct result. So, well, let's stick with the plus since this is what the script says. I am sure I thought about this. After tunneling. Yeah, so this is the kinetic energy, this is the potential energy. Okay, and then we can now introduce a few useful expressions. We will use the vector potential to find expression for the velocity, the location, and the Lagrange function. Yeah. Okay, I skipped the sentence here. Okay, so we'll use the canonical momentum. P plus EA equals constant. Yeah, so we can write V of t as the difference of vector potentials. Yeah, so P is the same as V, and the charge is -1 in atomic units. Yeah, so we get this expression here. So that's 1. The next one is x of t equals integral T0 to t over the velocity, of course. And so we integrate over the above expression there. T0 to t, a of t minus a of T0. And what we get then is x of t equals minus a T0, t minus T0, because a of T0 is just a constant. Yeah, so this would actually be our drift velocity. And now comes the oscillating part, and this would be the integral over the vector potential, a quantity that we encountered before. And then the Lagrange function after tunneling, L after tunneling, ½ a of t minus a of T0. So that's the velocity plus e times t, a of T0 t minus t naught minus integral from t naught to t a of t dt. So we have three expressions here using the vector potential. Okay. Good. So we, then the next remark is about, well, what we're actually calculating. Namely, so we're calculating, we're assuming that we have a multi-cycle pulse, yes? Because in a few cycle pulse where the envelope changes, then these, the amplitude here and there would not be the same anymore. And so the spacing of these two times would not be strictly t. Yeah, so this unnecessarily makes things more complicated. If we, however, had the other extreme, namely a CW field, then there would be no end of the pulse to which we can integrate. Okay. Yeah, so we assume multi-cycle pulse of finite duration. Yeah, okay. This comment we discussed, namely this is about the limits of the integration, and then we define now the oscillation amplitude. Oscillation amplitude alpha naught equals E times E naught divided by m omega squared. Now for a time-dependent field amplitude, strictly speaking, this oscillation amplitude alpha 0 would be also a function of time. Yeah. Yeah, because it goes to the end of the pulse and becomes smaller and smaller. But we will assume that in this range here, where these two are emitted, the amplitude does not change. Yeah, because they're somewhere in the center of a rather long pulse that has many cycles, so it does not change in between the two. Okay, anyway, so using the amplitude, we can write the velocity and the position as follows. Omega times alpha of t sine omega t minus omega alpha naught sine omega t naught, and then x of t equals minus alpha of t cosine omega t minus cosine omega t naught minus alpha omega t minus t naught sine omega t naught. The second term is again the drift velocity, and this is the, well, this actually is also, no, this one goes to 0, yes. So this is the oscillating part, this is the drift velocity. Okay, so you can make a cross check. So if you plug in t equals t0, then this becomes 0, and these two values are the same, so this goes to 0, and same, so this and this becomes the same, so it also goes to 0. Okay, so now we will finally calculate the phase difference. Yes, please. It comes from the envelope. Yes, because so the pulse looks something like this, right? Oh, no, I need to draw a long pulse. Yeah, so it goes to 0 somewhere, And we assume that these two peaks here, there may be those two. Yeah, so this is shown there. Yeah, and then if you think of the trajectory, as long as the field is strong, the electron oscillates very strongly. Then as the field goes to zero, the oscillation amplitude gets smaller and smaller, and eventually just the drift velocity is left.
So the time dependence comes from epsilon as a function of time, or where?
Yeah, so you can write the electric field as, maybe I should have assumed a finite duration. Maybe here I can write the epsilon E0 of t equals, so this is now the amplitude times some envelope function. This would be where this comes from. And now we have the cosine omega t. Yeah, and this f of t would be the envelope function here. Okay. Now let's finally calculate the phase difference. Calculate delta phi equals phi 2 minus phi 1. Oh, actually, there I did it the other way around. Phi 1 minus phi 2. Yeah, so delta phi equals 1 over h bar. So I'm plugging in now, these expressions here, with the Lagrange function, t0 to t end, L of x1 of t, dt minus 1 over h bar, t0, t end, L x2 of t dt. Okay, so this is simply the Lagrange function, and now I will plug in the Lagrange functions here. These Lagrange functions. So we have our 1 over h bar, t0 to t end, 1 over mv1 squared plus e of t x1 of t dt. Yeah, so this is phi 1. Sorry, this is this. Not phi 1, the first Lagrange function. And now comes the second one. Minus 1 over h bar. And now we need to take into account that the second trajectory only starts here. Yeah, so it goes from t02 or t0 plus t to the end. And then we need to consider this part where the electron is still bound. So t0 plus t to the end of the pulse, 1/2 mv squared plus e t x2. Sorry, this is the 2. X2 of t dt. I guess I could have and maybe should have added the time dependence here as well. So just consider it being there. You know what? I put it there. And here. Okay, now we need the second. Yeah, so this is now the part where the electron is still bound. Yeah, so minus 1 over h bar T0, and the Lagrange function is simply EIP. Okay, we will now rearrange this a little bit. Namely, we will, first of all, this here is that part. And now what we'll do is we'll put together the parts that depend on the velocity, and then the parts that depend on, well, the field and the position in particular. Okay, and that looks like this. M over 2h bar T0 to T end V1 squared of T dt minus T0 plus T to T end. Yeah, so this is now the second trajectory, V2 squared of T dt. Now comes the, so this is this bright green. Now comes the second integral, E over h bar T naught to T end, E of T x1 of T dt minus T naught plus T T end E of T x2 of T dt. And then finally we have just this term left, and we can readily integrate it. Simply EIP over h bar times the optical period. Okay, and now we, I forgot to underline this one. Okay, now we will take a look at these two terms individually. We also call this one here 1 and that one 2, and try to simplify those. Okay, so we have here A. Calculate 1. So we solve the integral from T0 to T end, omega alpha of T sine omega T minus alpha omega alpha naught sine omega T0 squared dt. And from this, yeah, so by the way, what did I do there? So this is I plugged in the expression that we derived here. Yeah? Or, no, I used the other one, this one here. Yes? So I plug in this expression, and that was only this first part. And now comes the second part here. No, sorry. This is, I used this expression. I used this expression here, but I split up this integral. Yeah, so this one integral goes from oh no, this comes after. Yeah. This is the second. I was one step ahead in my thoughts. Yes. So it's now simply comes the second integral. We'll just plug this in. Omega alpha of t sine omega t minus omega alpha naught sine omega t naught plus omega t. And then we have to square this dt. Okay. Now omega t, this is of course simply 2 pi. Yes. So this is nothing else but sine omega t naught. And then you see that this part is the same and that part is the same, and only these integrals only differ in their limits. Yeah, so this can be written as integral from t naught to t naught plus t omega alpha of t minus omega alpha naught sine omega t naught and the whole thing squared. Okay, so now we do what I mentioned, namely we neglect, we assume that within this short time range from t0 to t0 plus t, alpha of t doesn't actually change. Yeah, so between t naught and t naught plus t. Yeah, because we're not using a few cycle pulse. Yes, please. Maybe I forgot a no. Thank you. I don't know why I did that. Sine omega t. Yeah. Okay. Yeah, so if we do that, then we can rewrite 1 as follows. M over t. Oh yeah. So this was some rearrangement, and we skipped the prefactors here. Yeah, I skipped this prefactor previously. Now we'll use it, and so omega alpha naught we can now drag out of the integral. We just have to consider the square. T naught plus t sine square omega t minus 2 sine omega t sine omega t naught plus sine squared omega t naught. Yes, so just multiplying out. And now we can actually integrate. Yeah, so the integral over sine squared is always a half. And if you integrate over, if you have this omega there, then the result is actually t over 2. And now this is an oscillatory function, and we're integrating over cycles, so it's 0, and this is just a constant. T times sine squared omega t naught. Okay, so we can summarize here. 1 equals t over h bar up plus 2 up sine squared omega t naught, where up equals m omega squared alpha squared over 4. Yeah, of course, UP would be electric field squared. Maybe let me write it out. Yeah, so UP is E squared, capital E squared, 4m omega squared. Yeah, and then this we can rewrite using the amplitude like this. Okay, so this is our first result. Now we need to do the same thing for the second part here, and I have good news and or bad news and good news for you. So the bad news is this calculation is even more cumbersome. The good news is we're not going through it. I just give you the result, but you're welcome to calculate it yourself. I did it, and the result should be correct. And but the result is actually even shorter. It's minus t over h bar times 2 up. Yeah, and then we can actually now summarize. In total, delta phi, that's the sum of 1 plus 2 plus 3. I forgot, did I call this 3? I did not call this 3. But consider this being 3. And that is t over h bar 2 up sine squared omega t naught minus up minus EIP. And well, this gets a little box. Okay, now did we? Yeah, now you remember we actually assumed that the energy, which is given by 2 up times sine squared omega t naught, is an ATI peak. And so it's n times the photon energy, n some number, plus some energy offset. Okay, so, and we also said that the phase difference should be a multiple of 2 pi. So let's put this into our result in order to interpret the result. Okay, so let's first remember we had chosen. So this is what we are now referring to. Yeah, so these two formulas. The drift energy is 2 up sine squared omega t naught equals n h bar omega plus some energy offset. Yeah, now we have delta phi equals t over h bar times 2 up sine squared omega t naught minus EIP plus UP. I'll put this in extra brackets. Okay. Now, this is of course the drift energy, which is n h bar omega plus delta E. And this is simply 2 pi over omega. Sorry. I should rewrite this a bit different. So that's T over H bar. And only T is 2 pi over omega. And now the interference condition for a constructive interference is that the delta phi is a multiple of 2 pi, right? And now I plug in, so that's this condition here, constructive interference. Interference, okay, equals 2 pi n. Yeah, I write n. So here the T over H bar, I move the H bar inside and the omega as well. So it's n minus EIP plus UP H bar omega. Maybe it's better to first write the energy offset. So we have n plus delta E divided by H bar omega. And now we have this term is here. Okay. Now we get in the constructive interference if delta phi is a multiple of 2 pi. And here we get some number n, which is the number of photons absorbed, times 2 pi. And then we have these two terms. And so they must be equal. Otherwise, the equation is not fulfilled. And that means that our energy offset delta E is given by EIP plus UP. And this is what we expect. I forgot half of what I wanted to write. Delta E equals EIP plus UP. Exactly as expected. Yeah. So the offset of the ATI comb is given by the ionization potential plus the ponderomotive potential, exactly as we predicted using the photon picture considerations. Yeah. So this means we have now actually successfully brought together the two pictures that we have of strong field ionization, and this shows that our semi-classical model can really take into describe these dynamics and correctly produce the position of the ATI peaks. Yeah. The offset is given by UP as predicted. Okay. Now, okay, so yeah. Time's a bit too short to go through the rest, so I'll show you some results and to fulfill my explain my claims, unless there are questions regarding the calculations here. Yes, please. Sorry, what? Say again?
It's not here in that script.
What is not in the script?
The
The second
second term.
term. Yeah. I introduced this earlier today because I thought it makes sense to put this there. Because so in the script, the way the script is written, or the previous script, I actually uploaded the new version today. So the way the script was written is that it's assumed that the ATI peak position is exactly n times h bar omega, but that's not true, right? We did not take into account these offsets there. Yeah. So I thought this makes more sense. Yeah. Okay. Can you switch to the laptop, please? Okay. So these are some electronics that you can use to measure photoelectron spectra and things. Okay, so once again, let us just recapitulate. We looked now at the interference actually of these circles, for instance, yeah, because we drew it here and there on the falling side here of the field. We could have done the same for the triangles. This would be exactly equivalent. So now we connected these two here. So these make the ATI peaks. And yeah, next, I suppose probably next week we will discuss briefly these effects before we move on to harmonic generation. Yeah, and now in the following, I'd like to show you an experiment that has also been called the attosecond double slit experiment. Yeah, so that's this here. And here a few cycle pulse is used in order to drive ATI. Yeah, so you can make the few cycle pulse so short that only approximately 3 half cycles contribute. And so you can think of having on one side, so this is the vector potential, so on one side you have 2 ionization events contributing, yeah? So you actually have a double slit that can lead to interference, and on the other side, which means electrons emitted to the opposite direction, there's only one such event. Yeah, I mean these could also contribute, but they would only contribute at lower energies. At this rather high energy, only this one peak contributes, and then there's nothing that this can interfere with. So you also wouldn't expect any ATI peaks. Yeah, since ATI is a consequence of interference. And this is precisely what was shown here in this work. Yeah, so here, this is we would call this a minus cosine like field, which you would, sorry, this is actually not a field, this is the vector potential, so this is a minus cosine like waveform, in this case the vector potential, and this would correspond to a sine-like pulse, yes, and therefore you have the CEP pi over 2, and here you see on one side you see a strongly structured spectrum, and on the other side there's almost no ATI peaks. Yeah, so I say on one side, so this would be the signal from the right, or let's call this not the right detector, but maybe the upper detector. Yes, so this would correspond to this case, and this here would correspond to the lower case. Yeah? And so this shows that with a few cycle pulses, you can manipulate these interference effects, and this becomes really quite interesting. Now another manifestation of such an interference effect is shown here, which was published by our group here a few years ago. So they were looking at ionization of sodium atoms. So you can evaporate solid sodium, and then you get a sodium vapor in your vacuum chamber, and then they shot the laser at it. And they were looking at, they were recording the photoelectron spectrum that's here, and that actually has like a first ATI peak or a 0th ATI peak here, another one there, and a third one there. And shown as these false colors here is the asymmetry. Yeah, so the number of electrons emitted to the left and the right. And what you can see is you have basically a peak here and a peak there where there is no asymmetry, but in between where the two interfere, you get quite a strong interference. And this is because the phase of these two of the electrons that contribute to these two peaks now depend on the phase of the laser, which you manipulate. And then by doing this, you can either have constructive or destructive interference of the two of the trajectories that contribute either to this first or to the 0th peak. And when they interfere constructively on one side, they will interfere destructively on the other side for symmetry reasons. And then by shifting the phase of the laser, you can move the electrons going to either one side or the other side, and really observe really strong asymmetry in the electron emission. Yeah, and then, yeah, as mentioned, next week we will move on to the other interference effect, the intracycler ballistic interferences. And if you have, do you have further questions before we close the session? No? Okay, then thank you very much for the attention, and see you all next week.